Like now? Yeah. Okay. Try to repeat again. I'm the Huang number 3, and I'm here talking about the QubiC. So the QubiC, the key part we are trying to emphasize this is open source and it's full stack. This morning we heard from Professor Lin and also from Kel about both the error correction and also the application for the quantum computer, and how that this kind of thing looks like pretty different from what we are doing here from the mobile space and so from this conference, from the audience here. So, but there are definitely lots of good newspaper and great milestone has been achieved during the last couple of years. So both from the Google have been able to do the quantum supremacy, and also from the different from the neutral atom system, they have been able to demonstrating the bigger system to be able to manipulating, and by seeing this, there are already lots of different kinds of quantum platform. There are all the we have been working on the superconducting, so we listed them at the beginning, and this morning Lang also say why that is good. That have lots of potential, lots of possibility, and the big company like Google, IBM, and also people from MIT and lots of academia groups are doing the research on that part. But there are also lots of a big variety of the different platforms: trapped ion, neutral atom, and photonics, semiconductor, and center. So all these are all kind of potential things. The reason why they all still exist here and they'll still kind of reason to see which one is going to be the one in the future if we look down 50 years from now. So currently, yes, superconducting, maybe together trapped ion, neutral atom kind of leading the race. But 50 years from now, is that going to be the case? People typically try to animate it, try to analog the classical computer and the quantum computing, trying to thinking about at the early stage vacuum cube, is that really going to lead into the IC? Nobody knows. So maybe not, because on the superconducting, there are lots of great advantage, but still question mark. Then this kind of leading to which part should we research, and also from the different research area, how can we continuously pushing the front end of all the different directions. So like on the lower right side, there is a kind of the roadmap from Google. We kind of can see the first 2 milestones has been achieved, but there's still a long way to go to eventually go to maybe this is a tiny percent. So in a huge system to be a full error corrected fault tolerant computer, that seems still a long way to go. Even maybe that's reasonable, but among all these systems, no matter how quantum they are, no matter how they implementing a quantum system, we human beings living in the classical world. So we need a way to be able to communicating with them. And people has been developing all the different kind of control system to talking to this kind of quantum system, to be able to manipulating, to measure, to control these kind of qubits, these or that kind of qubits. And some of the systems are internal developed, like from the big company IBM, Google, or Quantinuum. So those things are great. I believe they have great performance, but nobody have access except them. And there are lots of I wouldn't say early startup, but kind of booming from the last 10, 15, 20 years. People have been generating all the different commercial available systems. Leading was kind of quantum machine, Zurich instrument, Q blocks. Those are all great systems. And also intermodulation products. So they all really great. They can do lots of things. But there is one problem, which is the one I showed in the previous page. We don't know what's the target going to be. We don't exactly know where the future going to be. So we want to be, as a researcher, we want to be able to explore all the different things, but whatever inside those systems is already fixed there. So you cannot really manipulating lots of them. And I've been trying to talk to lots of them to say, okay, you also have FPGA. Can I put directly load my FPGA code into there? No, that's their company proprietary system. So that makes the value for us. We are trying to see we need the whole community needs some open source system. And we from Lawrence Berkeley Lab developed this QubiC. We are not the only one. And there are also Kick from Fermilab. There are also an early generation for the trapped ion has been already kind of leading the market for the Arctic that has been there for many years. So in Lawrence Berkeley Lab, this team, we call the QubiC team, has been developed this system since 2018, and has since luckily we got support from the DOE through different grants. And first, let me try to see what are the challenges on the quantum control system, because this morning we heard error correction is important, and there are lots of really important math, and since there is one solution, Lin already saying, but how is that going to be implemented eventually to the qubit? How we can really do that? So we need this kind of system, and this system is basically is answering the question: what can be implemented where, or should be implemented where, or must be implemented where? So that's kind of the question. The system optimization. You need to think where should we do that? And there are lots of different things might be able to implement in here or there, but what we need is this kind of full stack access is essential for the system optimization, because you do not want to say, okay, I can access some software, but next layer, sorry, I cannot touch, so I can only talking that through the API. Then that's kind of limiting you. So that's where my philosophy I understand is full stack access is essential for the full system optimization. And look back about such a system, there's nothing fancy. So we kind of think, hopefully after my talk, people, if you are not working on quantum control system, you will get an idea. Oh, that's so easy. I can do that. Everybody can do that. So let me just go back to a regular software-defined radio architecture. So you have some smart. Nowadays, lots of them are FPGA, maybe ASIC for different speeds, maybe some MCU, and then you have some analog digital converter back and forth. And on those FPGA, you kind of have your digital signal processing, and some of them related with host configuration or something. Some of them related with whatever hardware you are going to manipulate. And on one side, you are talking to the real world through the RF or some. It is for us, we are using SMA going to a coaxial cable. But for maybe for the mobile, for this morning's the MIMO system, maybe different array of antenna. But those are the different signal conditioning eventually send the signal out. And the other side, somebody need to tell the system what you want to do. So that's kind of connection to the host computer through some kind of communication protocol, either Ethernet or some other thing. And every layer of this system, before we fully be able to optimize the system, we need everything. So for the hardware, we need low cost, low noise, and also scalable, because we are trying to get from 1 to 10 qubit to 100 qubit to 1,000 qubit, maybe to 1,000,000 qubit. And the gateway side, I call it gateway because it's on the programming logic of a system. We need to have low latency, be able to have a low level access, be able to optimize for whatever the quantum DSP, because if there are general things that's actually 20 years ago, or most of the physics lab doing that using AWG, they are good. They can demonstrate the basic thing, but the efficiency and also the latency and for transfer all those data, that's kind of become a bottleneck of the overall system. So we need the optimized quantum DSP. And in the firmware layer, which I typically say that's kind of something written in C or something, you need to be able to have low latency and providing the transparent. And you need to have some kind of software API to be able to providing the multi-level access and whatever human and machine readable configurations to don't get lost there. And also the optional visualization. So we have kind of seen this picture from Yang's talk this morning. This is a QubiC in the advanced quantum testbed in Lawrence Berkeley Lab, which is one of the two DOE quantum testbed. The other is Zandia for the trapped ion system. So here in this system, Yang has been emphasizing on this side, talking about, okay, here is our bridge, here's our system, and that's a chip. And we are trying to emphasizing this part of the system, which is the classical room temperature control system. Because for the cold one, there is another territory we need to tackle. So for the room temperature part, what we want to use some kind of FPGA. Be able currently the choice is an R system on chip, because that's thanks for the communication community kind of make the industrial partner be able to developing this kind of system. So that's another reason. So currently the quantum is great, but it's still not big enough market to influencing the big chip vendor. So thanks for the communication community leading to this kind of chip available. And so on the RFSoC, we have the DAC and ADC generating the pulse and to control the qubit, and also generating the readout and loop them back, going through the qubit and looking at what's the response of the from the qubit. And as I said, starting from 2018, we have been developing this system. At that time, this RFSoC does not exist yet. So we started from the Vertex 7 system, and the same requirement, but we can see the different generations, they have different, they are trying to meet the same requirement, but at that point, we have to develop a customized IQ mixer, being able to shift the frequency up and down. Is that really outdated or not? I personally continuously question that because I'm seeing even from AMD the direction is not definitely not continuously to developing products for quantum, like increasing the number of DAC and reducing the number, limiting the number of ADC. It's kind of more for the MIMO system or this kind of system. So we need to think this kind of maybe some of the analog signal conditioning still going to be needed in the next generation if we need more things. So I kind of like to keep them still in our portfolio, and then be able to, but there's something like a parameterized waveform generation and the pulse sequence reuse. That's something we call that's specific design for the quantum application. And this kind of command instruction and envelope buffer, also some a set of automatic quantum chip calibration that has been used for make the control people being able to calibrating the qubit, being able to interacting with the qubit without the involvement of the major quantum people or the major quantum chip people involved. So that kind of makes things more automatic. That's kind of another key point. If we want to scale up, everything must be more automatic. And by doing this, and then, of course, thanks again to the existing of the RFSoC, and looks like lots of both the commercial one and also the open source one moving to this platform. That's RFSoC system. And on this version, we were based on this U216 evaluation board, and because it is an evaluation board, so that number one is cheap. I don't know how the business model for the AMD, but they really sell that at the almost the price of the chip itself. So we can start doing things even at a fraction cost of from the big the different vendor from the hardware, and then. But we have to develop some customized analog front-end board. So we are going to dive into that a little bit later. And also, regarding the gateway side, we have developing this distributed processor. That is one of the key things happened in the last couple of years. Nilay Furtwala from our group has been spent a lot of effort on developing this. So the big problem, the big problem is solved is how where is the bottleneck when the upper layer have some decision, have some command to come in here. What's the most time efficient way to be able to distribute them to different things? The best way is okay, just a different processor, and then they are distributed. They can communicating through each other. Then that's the best way we can do now. And of course, there are also machine learning on FPGA because we are going to talk about that a little bit later as well. So here is the hero, this U216, and we have been working with this for a while. And so let's look at a little bit spec of itself. So it has a 16 channel of the DAC and the 16 channel of the ADC. So this is the third generation of the RFSoC. Compared to the first two generations, or mainly the first generation, it has been increasing the sampling rate for the DAC. So that kind of enables the superconducting qubit to be able to run directly using direct digital synthesizing using this chip, because a native frequency we typically sitting is somewhere between 4 and 8 gigahertz. So this frequency is a happy frequency. We are happy to land it there, and it also have it has a little bit lower sampling rate for the ADC, kind of 2.5 gigasample per second. But we have tested because our system, the bandwidth is not super high. Typically, in the earlier system, it kind of only have kind of 1 gigahertz bandwidth. So 2.5 gigahertz is okay if we do the undersampling. So we don't even mix them down. So we just undersampling them. That seems works fine. And it also has it's called the programming system. It's basically just have an ARM core. It's people here programming all the different embedded systems. So it's just an Arduino or a little bit better than that, maybe Raspberry Pi level of CPU. It's not a great system, but it works. And it also have a dual core real-time processor, different high-speed communication. And so that's our hero. And next to our hero, we have to have some other supporting team. So here is some analog front end we have been developed next to the ZCU216. So as we said, this have all those channels. These are those differential channels are sitting on those two connector. Those connector are differential signal, so that we cannot directly connect them to the SMA, which we typically use on the other side of the system. So this kind of balance 32 channel balance board, we just fan out them to all to the SMA, and we have another optional RF amplifier. We can add it on top of that, but that's good, but that's not flexible. Because one of the big things for the FPGA is we have all the channel, all the different tile, all the different channel. We want to be able, giving the development of the quantum processor itself. At the very beginning, people only stick at a fixed frequency transmon, so we only need RF. And then we start to need to add the tunable, be able to add the tunable, either the tunable qubit or tunable coupler. Those need some lower frequency or DC coupling. We still want to have a perfect timing together with all the other signal. So then to answer those requests, we say, okay, let's have another version of this analog front end. Let's make it more modular. The modularity is one thing I think we really emphasizing here. So you can see here we actually have a whole set of the board, and we give it some name. So on this side, it's called a diff carrier because it's just carry the differential signal from one side, from one connector to the other. I don't want to do anything more than that. I just want this stupid differential signal, and I'm trying to utilizing the philosophy, keep it simple and stupid, because whatever I'm doing there, I might be regret at some point. And then some kind of different kind of daughter card on this one. So that can converting the differential to single-ended from using different technology. So currently we have this kind, we have two kinds of AC coupled signal with or without amplifier, and 3 kinds of DC coupled amplifier. And we are evaluating currently. Looks like the winning one is using this, but the other thing also can be further explored. But after doing this, I only have the limited real estate resource. I only have tiny space there. I don't want to do everything, every single condition is there. So that's why we introduce another carrier board. That's another stupid board because it's big, but it's really so stupid. It's only 2 functions. It's just mechanically supporting a board and also providing power to whatever daughter card is going to be needed. So I think it giving stability, so that kind of makes it really be able to support whatever all the possibilities. And currently we have been developed the RF amplifier and the trigger I/O and the slow DAC on that. And of course, there is another hidden functionality on those is everything have a I2C bus. So everything, if we need, we can talk through each other through I2C in a slow fashion. So those are default in there. And put this kind of system in the box. That's kind of the basic for our latest QubiC chassis. And besides what the boards we have been talking about, there's also some power management and fan control and how to mechanically mounting everything into a 2U box, because we do like we said, we do care about the real estate inside the rack. If we want lots of channel in one rack, eventually people was IBM have demonstrated 1,000 RF channel per rack, RF channel. So we kind of calculate, okay, that might be doable, because in a 30 some U you need some 30 something channel. So it's possible. So
they also use RF sock, same RF sock.
Not same RF sock. I think they even one generation earlier. So they definitely also updating. And okay, there's one thing I don't want to miss is this kind of the cost. So because the evaluation board is not a price we set, is kind of coming from the Xilinx. You can buy that from DGK, kind of 17K something. And on top of that, it's just a box board and different thing. We estimate something 35, 40, 45 in that range. So that's kind of a fraction of the bigger control system, like a quantum machine, Zurich instrument. So it's a small fraction cost. Of course, you also sacrifice something, because we do not have 100 people team developing the user interface, developing to make that much more user friendly. But that's, I guess, that still fit in the academia research. This
$2,000 per channel. This probably like $10,000 per qubit control, right?
Depends on how you calculate, what kind of qubit you are talking about, and how many DC, what kind of coupling.
3 to 5
yeah.
qubit.
Yeah. So we do need some smarts on this kind of system. Not only the hardware, we need hardware, but we also need some smart. And one thing I like to emphasizing is kind of parametric waveform generation, because one of the limitation before was, okay, everything have to give them point by point, depends on to the sampling rate of the DAC. And but quantum computer people, they don't really necessarily manipulating each point. So typically it's kind of a simple amplitude modulated signal. And we have to have we have the carrier frequency, and then we have some kind of envelope. But one of the key points is they need to be able to adjust the relative phase for this pulse, next pulse. That's earlier in the talk earlier. That's actually some virtual Z implementation, and there are also, yeah. So that's what's needed. So we kind of try to get the minimal set. So I'm always trying to see what is the sufficient and necessary set of the command you need at this layer. So people have been developed different intermediate representations. So we also jump into that. So I try to not encapsulating into some other class to some particular language or something. I'm just trying to say what is needed at this layer. And our decision there is, okay, we need some timing. We need to see where the destination that signal going to be, what kind of information for the carrier, and what kind of envelope, and maybe there is an additional multiplier for the amplitude, so you can adjust. So with this kind of system, that's actually that kind of we have this kind of design from the first generation and continue to the second generation, and then you kind of can think, okay, if there is a pulse you want to generate, you have some carrier. Some carrier frequency, and so we if you have some signal, and one part is the drive signal, either the driving the qubit drive or some readout drive, and then go through the fridge, looking at the qubit a little bit to see what's coming out, and then go back to the ATC side to looking at look at the response. And if we including the trigger part in that, so different pulse will corresponding to different gate. So then that's where the timing information need to kick in. And if we continuously extract the carrier information, separate the carrier information and the envelope information, so the carrier may be able, we can just do that on real time, applying to point by point, and the envelope we have to store, we have to take that from whatever optimizer have to give us, and then we need to further extract them to some kind of command. Those commands, as we described a little bit earlier, to So then the information we have to transferring from the host computer to the FPGA will be kind of minimized. And implementing this kind of system, we have we come to the architecture of our QubiC system, and here we have the okay, let me see, where should I? So we have been talking about the different kind of signal generator part with to generating the qubit drive readout and all those kind of things, and they all managed by different distributed core. And at the beginning, we kind of mapping each distributed core to 1 qubit, but we not too long later we find the limitation, and then we kind of giving more flexibility of the different signal generator, and also more possibility of the state discrimination options. Whenever we have the state discrimination, those kind of information further sent back to the distributed processor, and where they can talk to each other, they can think about, okay, what I need to do next. So those are the things can be implemented to for the mid-circuit environment and feed forward. That's going to that is an essential part for either error correction or even fast reset and lots of the fancy part. So okay, we got one box which implemented all these features. We can generate everything, and then we have to have some way to be able to talk through talk from the host computer through the system and be able to let the FPGA to do the thing we want. So here on the processing system, either we can run the whole circuit through the pink, which is a Python for zinc, run everything there. But as I said, that CPU is not great. So it's good, okay, for the initial test, but later you don't want that. So you want a transparent layer, from the PS to the host computer, and then on the host computer use your whatever CPU or whatever capability on your CPU, maybe HPC, whatever. So there you can have the drop management, you can have the direct pulse level and gate level control, and also that gives you the interface to some higher level language. Currently, we have implemented for the TrueQ PyBSPI and also Open Custom 3, which is basically hopefully anybody already converting to that. That's partial supported through our system. And one chassis is good, but not enough. We want lots of them. So we have to be able to communicating between each chassis, and we have to synchronizing each chassis. So the pulse generation from one chassis to the other, they have to be they have to good enough to not interfere, not degrade the performance of a qubit. So here we have been using this kind of hybrid technology. Both the copper and the fiber are used in this kind of communication. And the bench test has been demonstrated what needed. We said just now, either from Ramsey experiments. So kind of you have the one pulse on this chassis, the other pulse on the other, and we don't see the single qubit Ramsey frequency or any change about that. So that kind of telling us, okay, we are good. And by doing this kind of multi FPGA clock synchronization, here is a little bit more detail about how we did the synchronization between the multi FPGA clock synchronization. So it's the same concept from everywhere, I guess, from the wireless and from the Ethernet, from the PDP protocol. So basically, you send something from one side, say what's my time and whatever delay, and you tell me back what's your time, and then we check. Oh, we are offset a little bit, so let's adjust it. So that's a standard clock synchronization approach for many things. So we also developed there, and this kind of clock synchronization has been demonstrated to be scalable, because we can kind of daisy chain the sync port and then to make them be able to talk to each other. And of course, we still find out the reference clock, but that is okay for our system because our system typically still sitting either in a rack or in one room, is not a kilometer apart. So if we are trying to go to quantum networks, there's different approach we need to apply here. But here, this is the easiest approach. And the multiple FPGA, they can synchronize together, but they also want to talk to each other, because one big thing is a mid-circuit environment. After the mid-circuit environment, or after you measure error syndrome, you send that through the decoder. You need to either do something or kind of as a feedback. So those information need to be able to pass back from where you are thinking, either some other external device or something local. So those things need to be sent back to our distributed processor to make the decision what next step we need to do. So here we have been implemented this kind of fiber-based communication between the chassis based on the AMD Aurora and using the GTY receiver, and of course that so currently there is one problem is data communication latency is still in the 100 of microsecond layer level. So that's not good. So we are trying to for this part, that's what we are seeing. So future, we might want to, even for this communication, also kind of hybrid of the fiber and copper, because copper, the latency is number you can find out, and the latency is better. And so that's something still work in progress. And for we got this system, and then we can continue to try to see, using this system, what can we do, and anything we might be able to explore something more than the current necessary. So one thing is how one challenge for the current system is the state discrimination, because at the beginning, down in the fridge, the qubit itself is clear about 0 or 1. But as soon as the signal coming out from the qubit itself, as soon as it's coming to whatever the cable, and then going through the first amplifier, that's start to adding all the noise, everything there. So all those noise is difficult to manipulate. So people have been developing all those quantum limited amplifier, try to tackle that. But even with those, we can see the two blobs are still at that size. So here the concept is there any way we can use some smart technology, maybe the machine learning, to do the state discrimination? Machine learning, people already kind of using that, using the using the machine learning module on the host computer, being able to do the state discrimination. But there is a latency of that when you have to pass all the IQ data to the host computer, and then to be able to do the discrimination, then send back. Then can we do that, do this machine learning on the FPGA for the state discrimination? So that is the work Neil and Elon has been working on this to have been designed this machine learning for on FPGA. And basically the training part is still on the host computer, so kind of train the model based on the signal taken from the fridge, from the real qubit. And then the inference part is the big part is here. The inference part is put on the FPGA, and so this kind of two-layer MLP for quantum discrimination has been developed. And the big accomplishment here is architecture is implemented on FPGA for the real-time inference, and the latency there is only 66 nanoseconds instead of you have to move the data from the FPGA to host computer and back. So that's a huge saving of that. And this is another important thing to improve the speed for the latency of the old mid-circuit environment and feedback. And based on this system, they have also demonstrated to if we have multiple level, and then the performance can even be further improved. And so this kind of let's see, the conditional bit flip, the Q2 is initialized and measured mid-circuit using mid-circuit environment, mid-circuit using this module, and the outcome discriminate subsequent operation on Q1. So this kind of combination of the different state discrimination results status, and then to be able to improve the readout fidelity, and be able to be able to run an experiment and to think about what's the status of the qubit is good. But unfortunately, at least for our system, it's not always every time you turn it on, it's right stays there at the same calibration you have been. So that itself is a research topic. How is the long-term stability of the qubit itself, and what's external environment going to affect that? How you are going to further stabilize that? So once in order to further analyze that, what we have been trying here is to develop some data storage and visualization platform. So here is a system developed by Devanshu, and basically generating the using the database technology to collect both the calibration data as well as the experimental data, and then store them for the future further analysis. Okay, so in summary, hopefully this talk I can bring this information. The quantum bit control system share lots of technology with telecommunication on the room temperature control, both the RF microwave, ADC DAC, and DSP, FPGA, SoC, clock synchronization. Hopefully you have been familiar with all this and found, oh, quantum control is just like we said, generating an amplitude modulated signal. And if you want to get into this or start to put your hands, get your hands dirty on playing with that, so then we have developed this QubiC 2.0 has been developed around this U216 evaluation board. So that is expandable to support higher channel count, support both transmon and fluxonium qubits, because we do both AC and DC, all those different kind of configuration. And also hardware gateway are designed in modular fashion, because we can foresee FPGA have really limited resource. If you choose this, you have to sacrifice something else. So make it modular, so make it configurable. And also a high-level API and interface enhance usability. The last thing I want to echo what I have said earlier, the full stack open source, hopefully that can enable more research and development. And I have two QR codes here. One is for our repo. The other is if you are interested, you want to get involved, please take a picture and scan that. That will go to our database to see people who is interested. And here is another picture of our team. And thank you for your attention. Any questions?
The programming and readout overhead is a key consideration. So I've heard of using frequency division multiplexer to multiplex the programming and readout. Are you doing that already? Do you have thoughts about that?
Depending on which part you are talking about. There are two parts. One is the qubit drive part. The other is the readout part. So for the readout part, we are already doing that. Basically, I think it's either we have different version of gateway, or actually it's configurable. So there are 4 channel, 8 channels. I think we have up to 14 channel, because we want to have 2 readout drive. The other is the qubit drive part. I think that itself is a research topic for the qubit development itself, because how they can fast switch or multiplex them at their level. So from our side of FPGA, I think we can, as you know, FPGA, we can generate any frequency combination we can. But whether that can deliver to the qubit itself, that depends on the qubit chip itself. So that itself is a research topic.
I have a question on the machine learning based inferencing.
Yes.
Do you use the analog samples or the IQ samples for that?
Actually, I think we are doing both. So the time series, that is, I think that has not been fully deployed. The IQ sample has been already testing. Most of the data are on the IQ sample, but the time sequence is also, I think there is a model there still under different testing.
Thank you for the talk. It's very impressive that the open source is going towards the quantum systems. My question is about the cost target, but you're using the argument that it's actually much cheaper than buy product from a commercial supply. I agree to that. However, from my experience building far less complicated open source hardware systems, even the simple ones, require a bit of a knowledge of someone building it, require some time invested into building it. So do you think that if you will take into account the cost of actually hiring a technician to build the stuff for you, will the cost argument still hold?
That's the part I don't know how to answer in the big broadcasting environment, but let me see in this way. So, okay.
I think you already answered my question. Yeah, go ahead.
Number one, if you have to do everything yourself, and if you do not have a technician be able to fabricate some PCB, be able to assemble some, do some sheet metal and do some assembly, that definitely itself is a cost. But let's imagine if the other thing is our hardware and software, we are fully open source. So we are kind of exploring some collaborator or some probability, maybe some entrepreneur, some startup might be able to take our IP of the design because the whole system is open source. So that means if somebody can pre-assemble the box for the end user, then hopefully that can lower that barrier that further. And by giving the cost and the IP is already available there. So I hope that the end user cost also can be much cheaper compared to any of those commercial systems. That's our expect. Hopefully that doesn't happen.
So out of a follow up the cost question, right? Using ARPSoc, I think I was talking to Rob Shonko. He was hoping that it can substantially reduce the control per qubit, but sounds like it's not much cheaper.
Compared to what?
Compared to what pre-ARPSoc, right? So I was looking at like he told me pre-ARPSoc it's a 20K per qubit before people use ARPSoc, but now with what you have like 35K for
16 channels.
16 channels. That's about 10K per qubit ish. So it's in the half of price.
10K. Sir, if
Right.
16 times 2000 is 32K, right? If 16 channel times
But-
2K is 32K,
But no, but it's
times 3K is 48K.
yeah. So each qubit will need multiple channels. Right?
Yes.
They need 4. Let's assume it's 4, right? Then you 35K suppose 4 qubits.
I think the original price for the 10K per qubit is also based on the transpond, so that's a single channel.
Right.
So that's not already take that factor into
Right.
account. That's my assumption. Maybe I'm wrong.
What do you see the trend? I mean, for that to be even lower, the ARPSoc is going to be bottleneck, right? That's the most expensive part. You didn't count your time into that.
That's thanks for DOE.
Yeah, but the bill of materials, basic ARPSoc accounts for most of the
Yes.
cost. Do you see there's the future the ARPSoc get cheaper?
That's a hard question for me because I'm not from AMD. Who is from AMD? But I do see the problem as RSoC itself. Their next generation is not continue increasing the density or reducing the cost. They are putting the effort on the AI, which is great. We also going to do that, and also increasing the sampling rate is going to be the 30 gigasample per second. So that's why I try to keep our first generation in the slides, because in case that's a problem, there are also the solution from the analog device from the sorry, it's nothing. From the TI.
Right.
So they have the chips for the RF DAC. So those might be able to be the.
So you're saying that the ARPSoc is expensive also because a lot of the digital computer resources there, which are not really useful for quantum control.
They do.
But you don't use all of it. You use all of it.
I think they do because our FPGA are really full.
Okay.
Our FPGA almost okay. There are different either the IoT or the memory or something. Every version we definitely hit the boundary of one thing.
I see. You're not talking about AI stuff, just
No.
for the okay. That's interesting. So there's I would think of if that is going to make it cheaper ARPSoc just for quantum computing. Right, not for AI, not for telecommunication. How does the ARPSoc look like? The ideal ARPSoc.
I do not think that's going to reduce the cost much.
I see.
Because current as of okay, they might be able to get the board cheaper. That's what I'm hoping, because if you to my understanding, I have not buy this ARPSoc chip itself, but we have buy the different series FPGA. To my understanding, if you buy even in the hundred or thousand quantity, the cost is not what their list
Right,
price. It's
right.
a small fraction of that.
Right.
So that's where I put the hop in, and then for the RSoC stuff, I guess we are going to stay on whatever they have until the RSoC is not good enough. Then we have to go to DI, all right?
Another one is if they can make move some of the ADC resources to the DAC.
That's not going to be the case, I guess.
Yeah.
We still need ADC. We are not going to have a pure DAC thing. I think some of them.
Think about this would be a material 35K. I would think about if you commercialize the design, the sale price is gonna be like 5 times higher than that.
I guess that's going to
For the startup to make money.
that's going to be the business model thing. So
Right.
If I'm hoping if somebody starts this, hopefully that can at the beginning can be more focusing on supporting the open source community, can be able to do that. Then hopefully that can grow bigger. Then that might be might be the future. I'm trying to take in the model, maybe people like RISC-V or something.
Right. So you know there is similar thing actually come from wireless. Just some food for you to think about. You know, at RISE, we have people build this Warp platform that's kind of programmable FPGA things for software radio. So they started this company, but the company they're selling the hardware, not much profit.
Mhm.
But the most thing they're selling is a service. So you use my board, but I also give you hours to help you set it in the office like that.
Let's talk about the business model.
I don't know. Yeah, that's just what the
but back to the quantum side, I think there is another example is Arctic. So they have also kind of doing the similar thing. So they sell the hardware not expensive, and they have been sitting there. So that's something I'm trying to hope that can be a role model.